Hello students, and welcome to the final lesson for Unit 8. This is on trapezoids and kites. So let's get started. The objectives of this lesson are to apply properties of trapezoids, as well as to apply properties of kites. So we'll be looking at both kites and trapezoids in this lesson. At the beginning, we're going to start off with trapezoids. So as a reminder, a trapezoid is a quadrilateral, right? This whole unit has been four-sided figures, with exactly one pair of parallel sides. So it is not a parallelogram because it has one pair of parallel sides. Parallelograms, as a reminder, have two pair of parallel sides. So we're moving on past parallelograms. So it has one pair of parallel sides. Those parallel sides are called bases, and then the non-parallel sides are called the legs, okay? And let me give you a drawing of what this would look like. So if we have our trapezoid, something like this. These two sides are parallel, so that's called base 1. And this would be base 2. And then the non-parallel sides are called the legs. Okay? Next, we have an isosceles trapezoid, which hopefully you remember is a very specific type of trapezoid. And what that means for an isosceles is the legs are congruent. So if we were to draw this one, it would look more like this. And hopefully you recognize the word isosceles from when we did our study on triangles. So again, we have base 1 and base 2, but now these legs are congruent. That terminology should be familiar. The difference obviously being that in a triangle we only have one base because there's only three sides. Okay, and then the midsegment of a trapezoid, hopefully this is also familiar to you from doing the midsegment of triangles. Midsegment of a trapezoid is a segment that connects the midpoints of the legs of the trapezoid. And so this is what that would look like. We draw a trapezoid, and it doesn't have to be isosceles. It's really any kind of trapezoid. So there's our parallel sides, and we'll call this A, B, C, and D, okay? And if I go to the midpoint of AD and the midpoint of BC and I draw a line, so we'll call that E and F, then EF is the midsegment, and that means it cut AD in half and BC in half. Okay, and we'll talk about a theorem that goes along with that. And finally, we have a kite. A kite is a quadrilateral with exactly two pairs of consecutive congruent sides. When it says exactly like that, that means it has to be two pair. It can't just be one pair. It must be two pair of consecutive sides. And so a kite would look something like this. And we would show the consecutive congruency this way, where two sides in a row where they touch, they make a vertex, would be congruent. All right, let's look at some isosceles trapezoid theorems. So these first three theorems are only about isosceles trapezoids. So first, if a trapezoid is isosceles, then each pair of base angles are congruent. Okay, so we talked about in its definition that the legs are congruent, but what that means is that the base angles will be congruent. And hopefully you remember that also from when we talked about isosceles triangles. So let me give you a drawing of what that would look like. So let's see, I have a trapezoid. And it's important to remember on trapezoids that the base is like the longer base doesn't have to be the bottom of the trapezoid. I think we tend to think that, but that does not always have to be the case. Okay, so we've got these parallel sides and these congruent legs. And what we're saying is that these base angles are also congruent. And GH right here, that's a pair of base angles. And then FJ down at the bottom is another pair of base angles. Okay, so that the pairs of base angles would be congruent. And then the way that we would write this would be that if trapezoid FGHJ is isosceles, then we can say that angle G is congruent to angle H, and we would also say that angle F is congruent to angle J, because those are each pairs of base angles. So both sets of angles are called base angles in this. We just pair them up. All right, our next isosceles trapezoid theorem is 6.22, which tells us if a trapezoid has one pair of base angles, of congruent base angles. So one pair of its base angles are congruent. So any trapezoid has that, congruent base angles. Then it is an isosceles trapezoid. Okay, so what that means, right, effectively is that if one pair of base angles is congruent, then the other pair must also be congruent, right? Because we know that from the last theorem that all trapezoids have two pair of base angles. But one way to prove if something is an isosceles trapezoid is just by if you know one pair is congruent. And so that would look something like this. And again, remember, trapezoids can face different ways. Oops, sorry, this is going to go a little more crooked. Okay, the bases don't have to be on the top or the bottom. All right, so we'll call that K. This will be P. Here are my base sides. Okay, those sides. And this pair of base angles, we'll call that one congruent. Let me give those a label. So we'll call this angle L here, or point L. Whoops. That's L. And this is M. So what we're saying is that if angle L is congruent to angle M, then KLMP is an isosceles trapezoid, just by having one set of base angles congruent. And we know that what that would eventually mean must be that K and P would also be congruent. We can take that from the previous theorem. That would be adding the two together. All right, our final theorem about isosceles trapezoids is 6.23. A trapezoid is isosceles if and only if its diagonals are congruent. So first let's talk about that if and only if. Remember, that's something called a biconditional. We talked about that earlier in the year. And so here's our example. We have this trapezoid QRST. We have the legs marked as congruent, and QR and ST are the bases with the sides parallel. So how this would work, being a biconditional, is we would say, well, if trapezoid QRST is isosceles, then QS must be congruent to RT. The diagonals have to be congruent. Likewise, we can also say that if QS is congruent to RT, then trapezoid QRST is isosceles. So we can use this to prove a trapezoid as isosceles, or we can also use it if we know one is isosceles to prove the diagonals congruent to each other. Next, we have the triangle mid-segment theorem, and this is just a reminder. Actually, we've done this before. I talked about it earlier, but as a reminder of this before we get to the trapezoid mid-segment theorem. So remember, with the triangle mid-segment theorem, the mid-segment itself is parallel to the opposite side and half its length. So how this would look in an example is, let's say we have this triangle. And this is not necessarily an isosceles triangle. When we get to trapezoid, it's not about isosceles. This is just true for any triangle or any trapezoid. Okay, so we have triangle ABC, and we're going to create its mid-segment line, which cuts AB in half and AC in half. Okay, and we'll call that segment DE. That segment has to be congruent to BC, and parallel to BC and half of the length of BC. So DE is parallel to BC, and DE equals half of BC. We did this, I think, in January, back at the beginning of the year. We worked on this material, so hopefully that is familiar to you, and we're going to use that as we go into the trapezoid mid-segment theorem because they're very similar. All right, so we have the trapezoid mid-segment theorem. And what this says is that the mid-segment of the trapezoid is parallel to each base, and its measure is 1/2 the sum of the length of the bases. And that's where it's slightly different from the triangle. The triangle only has one base, or one opposite side, so it's just half of that. But in this case, because there's two opposite sides, so two bases, it's going to be half of their sum, basically their average. Okay, so if I have, in this example, I've drawn trapezoid ACDF, and I've made BE the mid-segment. So how this would look would be, we would be saying, if BE is the mid-segment of trapezoid ACDF, then we would say BE, that mid-segment, is parallel to AF, and BE is parallel to CD. Whoops, I didn't write parallel. Sorry about that. BE is parallel to CD. And finally, what we would say in terms of its length is BE equals half of AF plus CD. Okay, so you have to add up the bases, AF and CD, their measures, add them together, and then divide by 2, and that will give you the length of BE. So make sure that you add those up. That's the difference, one of the main differences between this theorem and the triangle theorem. All right, we have our final two theorems, and they are about kites. 6.25, if a quadrilateral is a kite, then its diagonals are perpendicular. Now, we've talked about two other shapes, quadrilaterals, that have perpendicular diagonals. Do you remember what they are? They are a rhombus and a square. And a kite also has perpendicular diagonals. So we're going to add that to our list of those with perpendicular diagonals. So let me draw a kite. And we know from the definition of a kite that two consecutive sides are congruent. That's what makes something a kite. So we'll call this kite A, B, C, D, and we will draw its diagonals. That was a disaster. That's not much better, but a little better. Okay, so what we're saying is, if ABCD is a kite, then AC is perpendicular to BD. Okay? And our final theorem, yay, our final theorem for the whole unit. So at this point, if you have not finished your theorem list, you should be finishing that up. You should have hopefully been adding to it as we go. Our final one on kites If a quadrilateral is a kite, then exactly one pair of opposite angles is congruent. So, and this is different also from parallelograms, right? On parallelograms, both pairs of opposite angles are congruent, but in a kite, only one pair of opposite angles is congruent. And let me show you how this would look. So we'll call that angle K and angle M. And the opposite sides will be J and L. Okay, so how we would say this in this example is that if JKLM is a kite, then angle J is congruent to angle L. Now I want you to notice it says exactly one pair, which means two pair cannot be congruent. They both can't be congruent. So if J is congruent to L, then angle K cannot be congruent to angle M, or then it is not considered a kite. If both pair are congruent, then we're talking about a parallelogram. Okay, so that's one of the ways that you can tell the difference. All right, you've got a few sample problems to do, and the next video will walk you through a couple.